When a modern Linux server crashes or a critical process is terminated abruptly, the system often generates a diagnostic log. Systems administrators know this file as a core dump. Walk into a modern data center and you will find no cores. Today's data is stored in floating gate transistors and microscopic logic gates. To a modern software engineer, the term is a linguistic ghost. In the 1950s, the hardware was more tangible. Early mainframes relied on massive grids of hand-woven magnetic rings, the cores, threaded together by copper wire. Debugging a failed program meant printing the magnetic state of every single ring onto long sheets of paper. They were literally dumping the contents of the core for inspection. Decades after the last ferrite ring left the factory, the terminology remains. Modern cloud-based systems are still haunted by the physical mechanics of the 1950s. Data storage in a ferrite core is a matter of simple polarization. A clockwise magnetic field represents a binary 1, and a counterclockwise field represents a 0. Retrieving this data requires a mechanical intervention. To determine if a specific core holds a 1, the system sends a pulse that forces the ring to become a 0. If the core was a 1, the sudden magnetic flip induces a tiny voltage spike in a secondary sense wire, confirming the bit's value. But that same pulse leaves the ring erased. To keep the data from vanishing, the system must immediately fire a reverse current to restore the bit. This creates a narrow timing window. The hardware has to execute a write after read cycle to reconstruct the bit before the processor moves to the next clock cycle. Designing these systems meant managing a cycle of constant annihilation and reconstruction. Every logical read operation was a physical intervention into the magnetic state of the hardware. By the early 1950s, the United States military was attempting to build an automated radar network to track incoming Soviet nuclear bombers. The computing architecture of the time, like the MIT Whirlwind, relied on ceiling-high racks of vacuum tubes that failed constantly. National defense was impossible with hardware that burned out every 20 minutes. MIT engineer Jay Forrester proposed magnetic cores as a reliable alternative. To make them scale, he developed the coincident-current matrix, eliminating the need to wire every single bit individually. Forrester arranged the cores on an X and Y grid. He sent a weak half-select current down one X wire and one Y wire. This current was too low to flick any ring on its own, but at the exact geometric intersection of the two wires, the currents summed together. Only that single targeted core received the power needed to flip, leaving the rest of the array undisturbed. The breakthrough allowed for true random access memory. This provided the speed and stability required to build the semi-automatic ground environment, or SAGE. Each SAGE installation was a 250-ton machine using 60,000 vacuum tubes and 3 megawatts of electricity to track radar blips across the continent. The radar telemetry and trajectory calculations for this defense grid were buffered and processed within these mainframe banks. Ultimately, the detection of a nuclear strike relied on the physical reliability of millions of microscopic ceramic donuts. NASA required a memory architecture for the Apollo missions that was lightweight and could survive the ionizing radiation of space. They used core rope memory, a read-only variant. Instead of using magnetic flips, they wove wires directly through a core to represent a 1 and around the outside to represent a 0. This software could not be digitally flashed. It had to be physically woven. Expert seamstresses threaded the flight code into the hardware by hand. A single mistake with the needle would result in a permanent bug hard-coded into the spacecraft. This manual labor was tested during the Apollo 11 lunar descent. Overloaded with radar data, the computer began displaying 1201 and 1202 program alarms. The system was on the verge of total failure just thousands of feet above the surface. Because the memory was non-volatile and physically fixed, the computer could drop low-priority tasks and restart without losing its place in the descent. The mission survived because its foundational navigation code was physically woven into the hardware. Having the software hardwired meant the system could recover from a crash in seconds, returning to a known state with the data intact. Magnetic core memory requires no power to retain its state. Because the data is stored in the magnetic orientation of ferrite, it is immune to the effects of ionizing radiation and electromagnetic pulses. This durability was tested after the Space Shuttle Challenger disaster in 1986.
Recovery teams launched a forensic operation to locate the shuttle's IBM flight computers. The hardware had endured a high-velocity impact and spent weeks in corrosive saltwater at the bottom of the Atlantic. In most electronics, these conditions would lead to the loss of all stored data. But the Challenger's computers utilized magnetic core planes. When investigators pulled the modules from the debris, the memory was perfectly preserved. They were able to extract the final milliseconds of telemetry data from the surviving rings. The memory survived the destruction of the airframe, the impact with the ocean, and the saltwater immersion. The recovery provided a level of forensic data that modern semiconductors cannot match. In the 1960s, IBM standardized core memory for the commercial world with the System/360. They scaled automated manufacturing, making memory arrays affordable for global business. But the physical limits of threading wires eventually hit a wall. In 1971, the invention of single-transistor DRAM and the mass production of the integrated circuit ended the core memory era. The transition to silicon offered immense data density and lower costs, but we traded non-volatility for those gains. Modern DRAM stores data as electrical charges in capacitors that leak. To exist, it requires constant power and must be refreshed thousands of times every second. A core plane from the 1960s can sit on a museum shelf for 40 years and boot its original program perfectly on the first try. We have engineered a global infrastructure with nearly infinite capacity, but in that pursuit, we abandoned the physical permanence of the code that defied decay.